I'll begin. Dear Father, we thank you for this day. Again, Lord, I thank you for these students and for this class. I just pray to be with us today. Again, Lord, help us to glorify you in what we do, Lord. In your name I pray. Amen. Well, guys, I will try to say interesting things today, but I have not had as much time as I wanted to prepare for this. There's something to say about ideals, and I'm just not there yet, and I'm starting to run out of semester to do it. But come on. But there are a few tidbits left over from what we were saying yesterday that I'd like to talk about. One of them is just quaternions. So I don't know how much, the semesters run together for me sometimes, you guys, so it's hard for me to remember. Have I actually talked to you guys about quaternions in here? Ever? Briefly? Well, let's talk again. Okay, so what are quaternions? Quaternions are, well, there's a couple different ways to look at them, but essentially they're a four-dimensional real vector space, which is also an algebra. Meaning it's a four-dimensional real vector space, and there's also a way of multiplying these vectors to get other vectors. Now, one model for quaternions is these 2x2 complex matrices. You can look at 2x2 complex matrices in the form alpha, beta, minus beta conjugate, alpha conjugate like this. If you multiply two of these gadgets, you get another object of the same type, which shows you that this multiplication is closed. This particular kind of 2x2 complex matrix, if you multiply two of them, it begets a third of the same type. And if you add or subtract them, or scalar multiply them, real scalar multiply them, you also get another matrix of the same type. Furthermore, you can define a norm, kind of in the not in the sense of linear algebra, but perhaps in the sense of number theory. You can define the norm using the determinant. If you do the norm of Q, you get alpha, alpha bar, beta, beta bar. So in particular, if you were to look at quaternion matrices where the real and imaginary components of alpha and beta were natural numbers, were integers, it's fairly clear that this norm would be integer valued. All right? And it would be a multiplicative norm in the sense that we talked about. So that's kind of neat. Now, the properties of the quaternion algebra are what you're used to. Distributive, it's got associativity, it's got a multiplicative norm. However, much different than most of our examples, it's non-abelian. Q1, Q2 is not equal to Q2, Q1. So here's the usual notation. You can call this 1, this I, this j, and this k, and they satisfy the defining relation I squared equals to j squared equals to k squared equals to minus 1. All right, where minus 1 I'm understanding to be the 2x2 identity matrix with a negative. So you've perhaps heard this before. I squared, j squared, k squared, they're all imaginary units, quote unquote. They all square to minus 1. But they also satisfy these interesting intertwining relations, in particular that I times j is equal to k times I is j, and j times I is minus k. This is just like the cross product, right? Like in calculus 3, you guys saw I cross k is, I cross j was k, right? We put hats on them or something. J hat cross k hat was I hat. If you took calculus 3 with me, we put x hats and y hats and z hats, but whatever, I'm weird. You know that. So anyway, these basically define the quaternions in terms of generators and relations. I could say that the quaternions are basically real numbers adjoined with I, j, and k, which satisfy these algebraic relations. All right, so it's a particular four-dimensional space with this really pretty algebra. Hamilton discovered this in, I think, 1843. Actually, he was trying to find, complex numbers are really nice, right? Multiply two complex numbers, you get another complex number. Everything's got an inverse, right? If it's non-zero, complex numbers form a field, right? Oh, by the way, if you watched the help session from yesterday, I was at the end, I was like, I'm not sure, I'm a little bit uncertain if field really belongs here. I had a chance to consult with an expert. Yes, the field belongs there. And the valuation map, we can make it just any constant. Although we shouldn't call it evaluation, we should stick with divisor function. Valuation is yet something else. So if we make the delta for the field just to be a constant, then it automatically satisfies the division algorithm, because over a field, you don't need a remainder. You just always have division. There's no, just the remainder is set to 0 always, so it's just a stupid division algorithm. So yes, fields are Euclidean domains, they are PIDs, they are UFDs, they are integral domains, they're commutative rings of identity. They've got it all. All right, the field's very kind of at the center of everything. Anyway, just wanted to remove any uncertainty from the end of the help session yesterday on that point. Okay. Now, quaternions would also be a field. I mean, they are a division ring. Right? This is actually an example of something which is a division ring, but it's not a field. Sometimes quaternions are called a skew field, because everything non-zero has an inverse. However, it's not commutative, right? Because you've got I times j is equal to k, but j times I is minus k, right? So those are not equal. It's not commutative. Excuse me. Now, whenever I do this in detail, now Hamilton had all kinds of sort of, I think, almost metaphysical inspiration for doing this. I mean, Hamilton spent the better part of, I think, a dozen years looking for how to do this in R3, trying to find a multiplication of three-dimensional vectors where that multiplication had every non-zero vector having an inverse. Because assumably, if you could do that, then you get all the kind of nice bells and whistles you get for complex numbers. But in fact, that's impossible. There is no such structure that can be given to R3. R4, on the other hand, is very special in the sense that there is this quaternion structure that can be given to it, a multiplication in which every non-zero element has an inverse. But it comes at the cost of losing commutivity. Not quite as nice as the complex numbers. Okay, so here's the product of two arbitrary, well, these are not arbitrary quaternions. These are, you might call these spatial quaternions. They've just got x, y, z terms. There's no time. So we could think of quaternions as like time space with t and then x, y, z for the I, j, k, which are sometimes called versors. Anyway, if you multiply two spatial quaternions, you get these 9 terms, right? But the I squared, the j squared, the k squared, those are -1. So out pops this x1, y1, y1, y2, z1, z2. If you look at that, that's minus the dot product of the vectors x, y, z1, x, y, z2. So this has got the dot product of the spatial vectors x, comma, y1, comma, z1 with x, comma, y2, comma, z2, which is kind of neat. And on the other hand, if you look at the non-real part, the coefficients of I, j, and k, if you study these, you're going to find that those are actually the components to the cross product of the vectors x1, y1, z1, and x2, y2, z2. So the quaternion product simultaneously folds both the dot product and the cross product into one unified algebraic operation, which is really beautiful. Here it is, explicitly. Alpha 1, alpha 2 is actually equal to this. All right. So that's very, very interesting. And in fact, before we used vector notation as a point of history, we used quaternions, right? Scientists and engineers used quaternions for about 50 years, probably before the vector notation sort of took off and took over around the turn of the 20th century. I think Gibbs and Heaviside, some of these guys, they pointed out, you know, we don't need to use quaternions. We could think about vectors and use dot products and cross products, and it's kind of less weird. And apparently, they made that for us well. They made that point well enough that it set in, didn't it? Because we don't really talk about quaternions much anymore, do we? Yet we still have the IJK hat notation in our calculus textbooks, right? That's a historical shout out to Hamilton's quaternions, actually. It's also a really bad notation. But anyway, because why should it be IJK? I mean, honestly, those should be x hat, y hat, z hat. When you use Cartesian coordinates, you should x hat, y hat, z hat for your basis. If you're using polar coordinates, you use r hat, theta hat. If you use spherical coordinates, you use rho hat, phi hat, theta hat. These actually have, that notation expresses a specific and meaningful mathematical structure. If you use IJK, what does it tell you? It's this ad hoc notation we've all agreed to use. It has no information. It's just horrible notation. I shut up. That is obviously not abstract algebra I'm talking about right now. Get back on track here. Don't worry, I'll go over to make up for it. So if you take genuine quaternions, like a time plus a spatial quaternion, a time plus another spatial quaternion, and you take their product, then you've got like the time space term, time space term, time term. This one is the one I just showed you contains the cross product and the dot product all at once. And so in total, we get that. Now, excuse me. I'm getting to a point here. I think I've lost my... All right, then, okay, great. Now what if alpha 1 equals to alpha 2 equals to alpha? All right. So what if we took them to be the same? When you take the product of a quaternion... oh, and here's also another thing has just entered the scene. This is the conjugate of the quaternion. To take the conjugate of a quaternion, keep the real part unaltered, and you just swap out I for minus I, J for minus J, K for minus K. For example, the quaternion conjugate of 1 plus 2I plus 3J plus 4K would be 1 minus 2I minus 3J minus 4K. You just like complex conjugation, except you do it on every one. So at the level of my notation, that's what this looks like. I mean, this is the quaternion conjugate. So if I take the product of a quaternion and its conjugate, that's t plus alpha vector, t minus alpha vector. And then these guys just cancel because t is a real number, and these are the same terms. They cancel. I've got t squared. I've got minus alpha alpha bar. Now, the term in alpha vector with the cross product is going to be gone because the cross product of a vector in itself is 0, right? So the only thing that survives of the cross of this alpha vector term is the minus dot product, but then that minus and this minus give me a plus, and so there you go. That's another formula for the norm of a quaternion. It's also given by the product of the quaternion and its conjugate, which is very satisfying because this is just what we've used in our imaginary number fields, like the Gaussian integers, right? Z bar was the norm. Same thing can be done here. So this is the quaternion norm. Excuse me. Let's see here. You also have multiplicativity of the norm, because if you look at this being that, there's a property. The quaternion conjugate actually, it doesn't quite, it's not the one you know from complex, but it flips the order like that, which is kind of funny. See that? Conjugate of Q1, Q2 bar is actually Q2 bar, Q1 bar. And, but then this and that give me norm of Q2 squared. That's a real number. Swap it out front, and then you get norm of Q1 squared. So yes, there is a non-commutative aspect to quaternions, but it's kind of, in some sense, like a really mild non-commutativity. It's mild enough that we still get things that are true in the commutative context. It's just kind of a little bit over the edge of being commutative. So many of the things we know for commutative objects are still true for quaternions. Quaternions are kind of this bizarro, just borderline weird case where a lot of things still work as you're familiar with them at the cost of some sort of ad hoc nonsense. This brings us to the four-square identity, which, like everything else we've ever talked about in here, was discovered by Euler, and probably some Indian mathematician I don't know the name of. But there I'm just speculating. I'm sure the YouTube comments will correct me. Let's see here. I hope you're doing a good job on the camera work here, Chris, because there's been some controversy in my calculus 2 this semester. I mean, if you follow my YouTube, if you read the calculus 2 comments, I've got this like string of cameraman's an idiot, cameraman needs to get with it, and I like it. There's like this guy's left like a dozen comments about the cameraman. I was like, I told him, like, you know, it's just a student from the class. They whatever in there. So here we go. The product of the norms of two quaternions is the norm of the product. But what that means is that this sum of four squares times that sum of four squares is actually equal to the norm of this, which, by the way, is the sum of this squared, that squared, this squared, and that squared. And that is the four-square identity, which says that if you can understand something as the product of two sums of four squares, that you can rewrite it as the sum of four squares. There they are. Exciting, no? All right. So Euler found this in 1748 without the help of quaternions. And Euler was doing it in the interest of proving that the natural numbers can all be expressed as a sum of four squares. Every natural number you can write as the sum of square of four numbers. Not uniquely so. Give me a natural number. What? 8? All right. 2 squared plus 2 squared plus 0 squared plus 0 squared, I guess. I don't know. Do they have to be non-zero? I can't remember. I feel like this n might be, that's a good question. Are we allowing 0 in this discussion? Now I can't remember.
One, right?
What's that?
You have to for 1.
For 1, yeah. Yeah, right. You'd have to for 1. Good point. So before I show you some of the details of Euler's argument, we just take a kind of big look at the history here, which I think is interesting in and of its own right. This is my lecture 15 from number theory. So with the two-square identity, which I showed you guys last time, the history of it is pretty old. Diophantus, like 200 AD. I don't know how to pronounce any of these names. But he discovered a geometric argument for it in 1593, which is pretty neat. That's on my next page, my notes. De Moivre, Gauss, Euler, these guys found it in terms of like complex. And then at the very end of the sort of 19th century, Dedekind elegantly and cleanly derived it using the Gaussian integers. That's what I showed you last time. That's a 19th century argument. The four-square identity, Euler derived in 1748. Rodriguez in 1840, I think, well, I'm not sure if this is really part of the four-square identity, but it's related. I think Rodriguez did something related to the quaternions. I'm trying to remember. Hamilton, 1843, found the quaternions. And then Hurwitz integers were applied to give natural definition of four-square identity in 1896. So, let's see here. But the more interesting thing on this page is just a sort of an overview of what the possibilities are. We can talk about a norm division algorithm, good grief, algebra. It's a vector space over the reals paired with a multiplication, all right? And and it satisfies a multiplicative norm, okay? A norm division algebra. And it can be proved that the only norm division algebras are the real numbers, the complex numbers, the quaternions, and the octonions. And Hurwitz proved that only for n equals 1, 2, 4, and 8 does there exist an n-square identity, like we've looked at for n equals 2 and n equals 4. I guess n equals 1 is kind of dumb, but n equals 8 has something to do with these octonions, all right? So what's the cost of the octonions? I mean, for quaternions, we lose commutativity. For octonions, we lose what? Yeah, associativity. Past the octonions, there are things past that. There's things called Sidonians, and more generally, there's these Cayley numbers, which involves the same process as Cayley-Dickinson doubling, and those things fail to even be those things. I think they continue to be what's called power associative, which means that powers still make sense, but that's about it. They're what? Yeah, they're not a division algebra. No. Now. This proof, this Hurwitz theorem here, can be proved using essentially just linear algebra. I almost did it at the end of semester 2 years ago. Almost. It's a good thing I didn't. My course evaluations are bad enough as it was. All right. Here's the geometric derivation of the two-square identity. This is a 16th century calculation. If you take these two triangles, right, you can construct another triangle like this, where you take the sum of the angles for the angle, you take A1, A2 minus B1, B2, and A1, B2 plus B1, A2, and you can construct this third triangle from these first two. And you can prove that this is geometric. I mean, you can make a geometric proof that you can take these two and put them together to get that, right? But the existence of this triangle says what? It says that this squared plus that squared is equal to h3 squared, right? Where h3 squared is h1 squared times h2 squared, which is what? A1 squared plus B1 squared, and A2 squared plus B2 squared. So this is a geometric version of the 2-square identity. Do not ask me what the geometric version of the 4-square identity is. I can feel it coming.
Can you ask about the 8 squared?
Ah! I do not know that either. This we should not look at. It's hideous. Ah, hideous. Excuse me. The Hurwitz integers are the game which is played with the quaternions to sort of flesh out this 4-square identity thing. They're the sort of quaternionic. They're sort of a quaternionic cousin to the Gaussian integers. It's not just this. I mean, this would be the natural sort of Gaussian integer, quote-unquote Gaussian integers within the quaternions, right? Just take integer coefficiented quaternions. If that's a verb that you can use, I don't guess it is, but or anyway, let's not get into grammar. I'll lose. And the thing is, if you use this, it fails because they're not dense enough to support a division algorithm, is what I'm trying to get at here. So if you throw in half multiples, then you're okay. They're close enough together that they support a division algorithm. The details are annoying because of the lack of commutativity. You can find details of this discussed in Stilwell's number theory text. And but anyway, after you divide by 2, then this is a nice thing. It's got enough points to support a division algorithm, and it's also got the sum difference and product of Hurwitz integers are again Hurwitz integers. In other words, they form a ring, a subring, if you will. And the norm is also a norm in the sense that it's an ordinary integer, which means you can play the usual games you do about like classifying primes in the Hurwitz integers by looking at corresponding values of the norm. For example, this 7 plus I plus j plus k divided by 2, we could rewrite as this plus 3, and it's got a norm which is equal to 13, which means that this guy is a Hurwitz prime. Woohoo! Because if it had a divisor, that would correspond to there being non-trivial divisors of 13, which of course we cannot do because 13 is a prime in the integers. Now, I realize I haven't assigned you guys homework on it. Let's not get too far into the weeds here. There's a conjugate, of course, as we've discussed. And basically, this is one of the critical theorems here, is that if p is a prime in the integers, but is not a Hurwitz integer, then p is equal to the sum of 4 squares. All right, where these are, I guess these could possibly be half integer, right? I'm saying that doubling these objects, A, B, C, and D, are integers, which means it's possible that A is like a half, B is like a half, C is a minus a half, stuff like that, all right? But this says that the prime, if you've got a prime in the integers, which again is not a Hurwitz integer, then the prime is the sum of. Not being a Hurwitz integer means not a Hurwitz prime. Yeah, right. So suppose we got p. Well, I'm not going to get So the claim then is any ordinary prime which is not a Hurwitz prime is a sum of 4 integer squares. And the details are not that bad, but, you know. Sorry, there's the division algorithm is, it's kind of left versus right. There's in the prime divisor properties, it's a little bit sketchy. It's not quite standardized, this stuff. But eventually, we get to the 4 square theorem, which is that, you know, any natural number is the sum of 4 squares. And if you look into the proof here, it actually involves using these Hurwitz integers to get the different cases that come up. So, all right. Well, I'm going to stop looking at this if you guys don't mind. So, excuse me. So when's our test? Wednesday. All right. So I guess that means Monday is your questions, huh? So with that, I should probably try to shift gears here. Go back to chapter 4 and start trying to pick up the pieces, huh? Let's see here. First piece I see that we're missing, rational roots theorem. I never proved that, did I? Can we prove it? Can you state it? No? Yes? Theorem 9? It says, let f equal to a0 plus a1x plus a2x squared, plus an x to the n, be a polynomial in z adjoin x, right? Where what? A0 is not equal to 0, and a sub n is not equal to 0. All right, then every rational root of f has the form what? C over D, where what? Where C is a divisor of the constant, C divides A naught, and D divides A sub n. All right, so let's look at the proof of this. It's probably it's a good review. We've kind of gotten a little bit past this point in the book, right? But here it is. So if C over D is an element of Q, right? If that's a rational root, what does that mean? And we're going to assume, what he says we want to assume, what do we want to assume? Yeah, assume that the GCD of C comma D is what? Right. In other words, if it's 4/6, we reduce it to 2/3, you know? Make sure it's already in lowest terms. If that is a root of f of f, what does that mean? That means if we plug that in, we get 0, right? So we feed it to the evaluation homomorphism, which naturally extends. I mean, see, this thing drives me a little bit nuts, is that it really shouldn't bother me much. I mean, there's a natural way of evaluating polynomials on objects which are larger than the given home of the polynomial, right? Like, we could take the polynomial, the real polynomial x squared plus 1, you know? And yet, it's very natural to look at phi I of x squared plus 1, right? Say, well, that's I squared plus 1. You know, so the evaluation, because the reason for that, the reason this makes sense, and this is just a custom that we have, if you want to get really picky, I think when we defined evaluation homomorphism, we may not have actually allowed for this, but it's with the understanding that R of x is naturally viewed as a subset of Cx, right? Because R is a subset of the complex numbers, right? In fact, yeah, subring. Very good. So for that reason, it makes, in the same sense here, since the integers are, you know, a subring of the rational numbers, we can meaningfully evaluate f at a rational. Anyway, I'm not. No, I don't know why I'm fussing over this. None of you would have objected to me just writing this down. So. And then what can we do? So that's equal to 0, right? Because it's a root. And then what do we do? Yeah, multiply by, clear out the denominators, right? Multiply by d to the power n, and what do we get? We get a naught d to the n plus a1 c d to the n minus 1, right? Plus a2 c squared d to the n minus 2 plus plus an c to the n equal to 0, because 0 times dn is d to the n is still 0. Then what? Say again, but then what? So this implies that d divides an c to the n. And what else does it say? Right, if we look at, then, so what Kang said is good. What Alan is getting at is this sort of the counterpoint, which is, if you look at all this stuff, everything here's got a c. So c clearly divides this piece. Hence, it must also divide this piece, because we can put that to the other side and get this is equal to minus that, right? So this also tells us that c divides a naught times d to the n, right? But we assumed this, right? Which means that d can't divide cn. So if d divides this product, it has to be dividing a sub n, right? D divides an, and c divides a naught as, the greatest common divisor of c and d is 1. Oh, and that's the rational roots theorem. So I think you probably you could prove this without abstract algebra, right? This is something, if I was teaching a high school algebra course and I wasn't pressed for time and I had time to actually tell the kids about what I was doing, I'd probably go through this with them, Because I don't think it's really requiring high-powered abstract algebra, does it? Not really. Yeah, I think that's probably the fussiest part. That if I was teaching high schoolers, I'd probably want to actually get out some numbers and show them how that works, right? Because the idea of divisibility might be not at all clear to them. Yes? Yeah, it should be. It should be part of the high school curriculum. Right. All right, another thing that should be refreshing for you guys. So these should be fairly relaxing compared to some of the things we've been looking at lately. Example 1, but I think they're worth doing, so I'm doing them. It's example 1 on page 215. Let's just go through it, though. Every linear polynomial is irreducible. So F is a field. So, all right. So what's a linear polynomial? Let F equal to Px plus B, right? And to see whether or not that's irreducible, what should we do? Yeah, or, well, basically, but suppose it can be factored. So it depends on whether you want to take a positive, it depends on your philosophy, whether we're actually looking to disprove it or prove it. I mean, if I can show necessarily that the factorization has a unit, then I'm not sure I'm really doing it's one of these things where you could either go contradiction or not, you know? What do I want? Say G1, G2, yeah? So suppose it has a factorization. To prove it's irreducible, we need to prove that G1 or G2 is a unit, right?
We know the leading coefficients are units because it's a field, so we can say the degree of the product is sum of degrees.
Okay, so the degree of Px plus B has to be equal to the degree of G1 plus the degree of G2.
And we would have that just from the fact that F field and has
Yeah.
domain. So either one of those.
It's definitely true here. So the other, I think you're right. We had the degree formula for a domain, right? Yeah. One of the things, again, like one of the things that's impressed me about this book is his attention to these kinds of details. You don't find that, like a lot of books just say everything's commutative from the outset and kind of go with it from there. He at least has a little discussion of non-commutative things. Just enough to annoy the students, I guess. But so this is one, right? And your choices, you only have two choices, right? So hence, degree of G1 is equal to 1, and degree of G2 is equal to 0, or the degree of G1 is equal to 0, and the degree of G2 is equal to 1. Those are the only possibilities because the degree there has to be is a non-negative integer, right? Now, I guess I do need that, I need to know that G1 and G2 are non-zero, right? So just, there's some fine, for a problem like this, we should actually say these things because it's, you know, the whole point of the problem. It's an elementary problem. Elementary details should be in it, right? Let this be linear. So what does that mean? That means in this context that P is not equal to 0, right? And how to say, I mean, if I want to, this is not terribly exciting, but P and B are where? In F, right? So if, and then I guess the thing I'm missing here, my solution's incomplete. Let me add the sentence right here where it kind of belongs. Notice G1 and G2 are not equal to 0, since if G1 is equal to 0, then F is equal to 0, right? Likewise, G2 equal to 0 implies F is equal to 0, right? And that contradicts the fact that If f is 0, that forces p to be 0, right? Both of these contradict p equals to 0. P not equal to 0, rather. You could write this better than I can, I think, yes?
If you wanted to write that in a proof, would you say something about x being indeterminate?
If I was going to write this in a proof, I should write like sentences and so take my thoughts and put them in order. I'm trying to say. Let f be this with p non-zero. Suppose it has a factorization, right? Notice that the factors must be non-zero, because if they were 0, that implies f is equal to 0, which then implies p is equal to 0, but we assume p was not equal to 0. That's a contradiction. So we must have non-zero factors, which means that as f, g1 and g2 are not equal to 0, we have... See, if the polynomial is 0, we don't have a defined degree, is my point. So if I'm going to use the degree formula, I do need to know it's non-zero to be picky. So this is that, and, again, the degree function is a natural number, or 0, and so it forces this, hence either g1 or g2 is constant, and hence a unit. Now I forget, and what does that mean? F is irreducible, yeah. Now if you choose wiser sentences, I'm sure you could wrap a lot of my thoughts into one sentence, rather suppose I put them into 17, all right? But now, if you just wrote what I wrote in the black, you'd probably have about 80% of the credit, right? But the finer points are what I put in blue. I'd really like to see both from you guys if it was this kind of question, But if I see the black, at least, then I know that you have the big idea, even if you haven't sort of crossed your I's and dotted your T's or whatever. Let's see here. Something seems wrong with that. Let's see here. All right. There's some very nice examples in section 4.3. I've already done some of those. I would like to just go ahead and skip ahead to the one theorem which is most interesting, and I haven't stated yet, and it's really kind of this theorem, if I have to say any, this theorem probably best gives you a window inside Math 422. And sort of the next large story arc in this two-semester sequence of abstract algebra, the next thing we'll probably cover is Galois theory. And this is kind of at the base of all that, this idea, this theorem. This is Kronecker's theorem. And we've kind of already seen this. We've seen this in play. Kronecker's theorem, what's it say? It says, if f is any field, all right, and f is a polynomial over the field with the degree of f greater than 0, positive degree, then there exists an extension field of f in which f has a root So what's an extension field? You might call it E, right? E is, it contains F, right? And it's a field. E is a field which naturally contains F as a subfield. That's what makes E an extension field of F.
So is this like if you have like x squared plus 1
Yeah,
as a real polynomial that has no root,
exactly.
but in complex numbers it does?
Yes, this is an example of Kronecker's theorem in action. X squared plus 1 is in R of x, no zeros. But f of I, of course, is 0. And yeah, so C is an extension field of the reals in which that has a 0. Now, here, let's just so let me sketch the proof for you. I think we've done most of the ingredients we need to do this. So you take a polynomial, right? Let's suppose f of x is a polynomial over the field, right? Then f of x is equal to p of x times g of x for g of x, well, for p of x, what? So we have proved that polynomials over a field form a unique factorization domain, right? They're a PID and hence a UFD. So we know that every polynomial over a field has a factorization into irreducible polynomials. I'm using that it's got positive degree, all right? So I know that there exists a p of x that's non-constant that's in the factorization of f, right? So p of x is irreducible. Then all you do is you consider f of x mod the ideal generated by p of x. All right? That is a field. Why is it a field? It's a field in which p of x bar, if you will, is identified with 0. I mean, maybe I have to write some more to make it completely clear to you guys, but, if we have the decomposition of the polynomial is, well, as usual, out of time, but why is this a field? Because that's irreducible, hence maximal. We have integral domain, mod maximal ideal. This is a field. And this is a field in which that is 0, but it's also a field in which f is naturally a subfield. If I think of this thing as being E, all right, then f is naturally a subfield of E, where how do you identify f as the subfield in here? It's with the constant polynomials in the quotient. All right, so it's an extension field of f, and by construction, this makes p of x be 0, x bar be 0, and consequently, f of x bar, if you will, is equal to p of x bar times g of x bar, but that's 0. That's it. That's how you do it. So it doesn't matter that other polynomials aren't irreducible, because you can always find an irreducible factor and from that form a field which forces that part of the polynomial to be 0, and that's all you need. This is Kronecker's theorem. There is a slightly more careful explanation on page 233, give or take. But don't worry, I'll prove this again next semester in more detail. Some of you will be there, I think, yes?